Welcome to one more episode. My name is Felipe, and in this tutorial session, I will go through the development process of deep learning based algorithms for AI soccer. Again, a little introduction about soccer. When we are young, we learn how to chase the ball, but we don't know really well about tactics and other soccer details. As we watch the game and as we are developing, we are learning that what's the best positioning and other really important knowledge regarding the game. Our objective here is to do the same with AI soccer and teach robots how to learn better and better behaviors throughout time after they're trying new strategies. In here in the AI soccer we have two types of robots, the junior robots that are the smallest ones and the big robots that are the senior robots. And the game is played 5 robots against 5 robots. The teams that score more goals win, similarly to a soccer game. In the AI Soccer API, the AI Soccer simulator is built in the WebBot Robot Simulator and communicate with both teams, the AI programs that are developed in Python. At each time step, the gamer receives the global coordinates and orientation of the robots, and the game state, if it's a penalty or a corner kick, they score and the time, and when a reset happens, the reason for the reset. For example, after my team scored, the game is reset in the initial position. Before the game starts, you also receive the important game information like the field, dimensions, and the robot specifications. You can use all of this information in your AI program to send back to the simulator the control variables for your robots to move and to achieve the desired behavior. These variables should be set in each time step for each robot. So you can think about your robot should move, should kick, and should jump. In order to achieve that, the 6 variables are the left wheel and the right wheel of your robot, because the robot uses differential wheels, 2 wheels to move throughout the field, the front slider height, the bottom slider, and the dribble mode. So you should set the 6 variables to control your robot. You can get more details regarding these actions in the AI Soccer manual. So, solving this problem with deep reinforcement learning is challenging, and it has a lot of room for improvement and building new algorithms. How deep reinforcement learning works. You have your environment, that in our case it is the AI Soccer simulator environment, and from the environment you receive your state and you also receive a reward. And the agent tries to map the states, like from the states, choose the action in order to maximize rewards, that we'll receive in the future. For example, in the soccer game, the agent will try to take actions that leads him to win the game at the end. And the big difference regarding deep reinforcement learning is that you map the state into action using a deep neural network. So you try to train a deep neural network to learn automatically to decide based on the state which action the agent should choose. In this case, the robot, to where it should move, if it should kick, or if it should jump. Deep reinforcement learning has been achieving breakthrough results, for example, playing video games. And in 2015, for example, it achieved better than human performance playing Atari. When you're playing a video game as a human, you watch the game state, that is the screen, the video game screen here that you see, and your brain choose which action to take in the controller. And your reward is based on the score in the game. Something that makes sense. And what the did to solve that was putting the neural network to choose the action, was trained successfully and achieved really good performance. And we're going to try to do the same for AI soccer. Here we have our AI soccer environment, and the reward, for example, can be our score or can be different. And in the rule-based algorithms, use our knowledge regarding soccer to choose the action, but we don't want to spend a lot of time designing rules for our rule-based algorithm. So we're going to try to put a neural network to try to predict the actions for us. But we see here that we have three main components in the deep reinforcement learning algorithm: the state, the action, and the reward. And how to design these three are really important to being able to train effective deep reinforcement learning algorithm. So we'll go through this designing a good state, a good action, and a good reward model. For the state, we can think that the best state possible is using all the information that we receive from the simulator. But using all the information is a lot of information for the network to decide which information is relevant and which information is not relevant. So we kind of simplify the state design for the robots. For the goalkeeper, as the goalkeeper, main focus is to protect against opponent's score. We define the state being his position in relation to a defensive position. The defensive position is the position that he can block the opponent kick, and his relative position to his own goal area, the relative position of the ball also related to the own goal area, his orientation, his arrow orientation related to the ball, and the ball velocity to know where the ball is moving. You can also try different state designs: state, reward, and action design. For the defenders, we try to give them the relative position to the ball, the relative position to his teammate, where here his teammate is the other defender. So one defender knows the location of the other defender. He knows the location of the ball in the field, his orientation, his arrow orientation in relation to the ball, and the ball velocity. And a similar state is designed for the attackers, but the teammate for one attacker is the other attacker. So they know all this position when they need to take their decision. You can think also using relative position as a player, that what he's able to see when he's in the field. He's able to see his surroundings. He does not have like a global coordinates of the field to take his decision, and we use the same idea and the same approach to design the state for our robots here. The next is designing our action. We saw before that to control our robot, we need to set 6 continuous variables in each time step for each robot. But as these actions are continuous, there are infinite possible combinations in this action set. Define our left wheel, right wheel, our sliders values, and the dribble move. So in order to make the future exploration easier of your deep reinforcement learning algorithm, we are going to discretize and choose just a set of possible actions for our robots. What are going to be these actions? For the goalkeeper, 13 discrete actions are defined, and we try to get the behavior of go forwards, and here these two are 1, 1 because I want maximum velocity. 1 represents maximum velocity. 0.2 represents 20% of the maximum velocity. So I have the go forwards behavior, the go forwards and pass, where the pass here in the third one I have the value for 5 for my front slider, that's half force for my front slider. I have go backwards, rotate left, rotate right, jump left because the goalkeeper can effectuate defense jumping for each side, and that are defined as my actions. And you can see here also the code for that, the matrix that define my discrete actions. For my defenders, also 13 discrete actions, and the same idea is given. The difference is that for the defenders, I also give some chance to cross what it looks like more a shooting behavior, where the robot kicks with maximum velocity in the front slider and maximum height to achieve like a high kick. So the defenders go forward and pass, go forward and cross, go backwards, rotate left, rotate right, and also can be stopped. For the attackers, similar actions than the defenders are used. And finally, we have the reward design. And the reward design is the most important when developing the deep reinforcement learning. It's really hard to get a good reward design to train effectively the robots. Sometimes you get a reward that you think that's going to work really well, but when you try the algorithm, it doesn't work as well as planned. So here I go through a little bit the reward design that we use in our examples. First reward is protect against kick. So the goalkeeper tries to protect against opponent kick. So they receive a bigger reward if they are in the position that is in the trajectory between the ball and our own goal to protect the kick. If they are far from that position, it means that they cannot block the kick, so they receive a smaller reward. The second behavior that we want to obtain in our reward design is like chasing the ball. So we calculate the distance between the robot and the ball. If the robot is close to the ball, he receives bigger reward, and if it's far from the ball, it receives smaller reward. To help the robot chase the ball, we also give a bigger reward if the robot is oriented towards the ball. If there is a high error in orientation between his orientation and his position to the ball, he receives a smaller reward. And to get soccer-like behaviors like pass, shooting, we also give, and also defending, we give two kinds of reward. The first is regarding passing and kicking. If the robot kicks towards its own goal, its own field, it doesn't receive any rewards. But if he kicks towards the opponent goal, he receives bigger reward if the kick is in a good direction toward the goal, and he receives a smaller reward if it is in other way, like kicking to the corner but in a trajectory that the ball is going to the opponent goal or to the opponent field. And we give the score reward, that when we score we receive a positive reward. That's our main goal in soccer, that is the score to win matches. And we receive a negative reward if the opponent is score in our goal, as we want to avoid this kind of situation. So for the same state, action, and reward design, we can use different algorithms to train our team. In soccer, we want cooperation and also to be competitive against different opponents. That's why it's a hard game. But here, in our most simple example, we try to just use independent learning where each robot tries to learn individual rewards. He just tries to maximize his individual rewards. So for example, the goalkeeper will try to maximize the protect against kick, and he will try to avoid situations where the opponent score. D1 and D2 try to learn to chase the ball and to move the ball away to give counter attacks, and our attackers try to kick and try to score goals against the opponent using individual rewards. So we have our deep reinforcement learning framework replotted here, where we receive our state and reward for the environment, and we choose our actions based on that. And this is implemented in the multi-IQL example in the examples folder, so it can run based on this architecture actually. I'll do a code review later to review this example. In this example, if you're curious, the network that we use three layers of 64 neurons, and the state that we showed before has 10 dimensions, has a 10 dimensions, and that we have 13 discrete actions. That is the output here of the network. So we are training a network that has the real size that I'm showing in this slide. But how do the robot learns how to play if you're not teaching him anything? Actually, he learns by exploring in the environment. At the beginning of training, he doesn't know anything, so he should explore a lot. So as we don't know anything, we just do exploration. So our exploration rate is really high. We take random actions. But as the training proceeds and we are learning which actions are good and leads to bigger rewards in the future, received in the future, we give more power to our policy that is being learned. So like you're getting better, so you have more power to choose action in what is called like the E-greedy algorithm. So we have the epsilon rate, and this epsilon rate is decreasing toward training. At the end of training that our policy really learn the desired behavior, it has all the power to choose actions and just exploit. And for example, when we want to use the trained policy, he chooses all the actions. We choose all the actions in what's called exploitation. So this exploitation is really important for you to learn the desired behavior. Here I show the reward graph for a policy that was trained using the state, action, and reward design that I presented for 1 million iterations. And you can see that at the beginning, when it takes random actions, the average reward is just 1.5. But after the policy is learning and it has more power to choose the actions, the reward is almost 3, almost double from a random policy. And the robot is able to learn how to chase the ball and also able to learn behaviors such as kicking. You can see here that the ball is here, but the robot chase the ball and then kick in the opposite direction and is actually able to score. What are the challenges of developing deep reinforcement learning algorithms? So the first one that I present is how to generalize for different opponents. At the beginning of the training that our algorithm is really bad, we should play against a random walk, so we have freedom to learn some basic behaviors. But as we get better, we also need better opponents. So we need to play against ourselves or play against other opponents so we can generalize and get a good strategy, a strong strategy. And what's the best way to design the reward function? Because actually the best reward function would be just using the score and concede for the reward, but actually if you just use that reward function, we're not able to learn because we are not able to score at the beginning of training. So that's why we need some curriculum reward that we first learn how to chase the ball, then we learn how to kick, and then we learn how to position and do some more complex behavior. And also to learn special plays are hard, special plays that do not happen very often during training, like corner kicks and penalty kicks, so they should be trained separately. Also the goalkeeper, because the goalkeeper, if you train against random walk, he cannot learn effective strategy, he should learn against a competent opponent. Exploration exploitation that I presented before is also a challenge, so you should know how many exploration you need to learn effective policies. And the training time. I train for 1 million iterations a graph that you have seen, and that is around 1 day training. So to train, you probably need to train for some multiple days to get a good algorithm. And also, multi-agent cooperative intelligence is really hard. Because as the environment is affected by your opponent, so you should get cooperation between robots and also being competitive. So it's really hard for them to train cooperation in this kind of environment. So you should try different algorithms and, for example, knowing the action of your teammates and knowing the global state to try to get multi-agent cooperation. And this was one more video of the iSoccer tutorial series, and see you in the next video.